Alrighty, hello everybody. Welcome back to Game Theory. First things off, yes, I've come down with COVID-19, so I apologize. We cannot have class in person for Monday and Wednesday this week. Yeah, it sucks. I apologize for having to do class this way. I think this is probably the best way to do it rather than trying to do it synchronously when we kind of haven't set up for that ahead of time. So I've made some notes on the board, and this is going to be a sort of shorter than a typical class, a little mini video on picking up where we left off last, good golly gosh, Wednesday. But before that, suppose two lines are caught outside in the rain. What should they do? Well, clearly, if the two lines are caught out in the rain, they should coincide. All right, let me make sure this is still working. Looks like mosquito. So let's pick up where we left off last time. So this is towards the back of the dominant strategies packet, for those of you following along in the packet. So last time we defined two different types of dominant strategies. The idea of having a strongly dominant strategy for a player, where that strategy is always giving the strictly highest payoff in every possible circumstance. And also the idea of having a weakly dominant strategy, where your strategy always does at least as well as every other strategy, and there's always at least one circumstance where it does better. And so if we apply these ideas to the standard and uneven prisoner's dilemma, we can see that in the standard prisoner's dilemma, that player 1 and player 2 both had a dominant strategy of confess. With the reason being that confess, for say player 1, will always give a strictly higher payout than deny does for them. So if player 2 chooses deny, then player 1 choosing confess gets 0 as opposed to -1 for deny. If player 2 is choosing confess, then player 1 can get -8 from choosing confess versus -10 for deny. So it's always strictly better for player 1 to choose confess in the standard prisoner's dilemma, and that's going to make it a strongly dominant strategy for both players. This one's a symmetric game. So we also discussed last time the uneven prisoner's dilemma, where prisoner 2 is moving after making their choice with knowledge of prisoner 1's choice. So prisoner 2 has more strategies. And we said that in this game, player 1 does not have a dominant strategy. The reason being, if prisoner 2 is going to choose the mirror strategy, it's better for prisoner 1 to deny than it is to confess, because they get a payoff of -1 as opposed to -8. But in every other circumstance, it's better for player 1 to confess, with the reasoning that if player 2 always denies, player 1 can get 0 as opposed to -1 by confessing. If player 2 is always confessing, player 1 can get -8 as opposed to -10 for confessing. And if player 2 is doing the anti-mirror strategy, player 1 can get a payoff of 0 as opposed to -10 by choosing confess instead of deny. So player 1, prisoner 1 has no payoff, has no dominant strategies in the uneven prisoner's dilemma. We did, however, say that player 2 had a dominant strategy in the uneven prisoner's dilemma. And that strategy was always just confess. The reason being, always choosing confess for player 2 always is going to tie for the best payoff. 0 is, if player 1 chooses deny, 0 is the best player 2 can hope for, which they can get from either choosing always confess or anti-mirror strategy. And if player 1 is choosing confess, then the best payoff player 2 can hope for is -8, which they can also get from either confessing or using the mirror strategy. And this time, confess, always choosing confess for player 2 is going to be a weakly dominant strategy, with the reason being confess doesn't always, choosing always confess for player 2 doesn't always give the strictly highest payoff. In fact, it ties for the best payoff in each case. Player 1 chooses deny, confess ties with the counter-mirror strategy for best strategy, and if player 1 chooses confess, always confess for player 2 will tie with mirror strategy for giving player 2 the best payoff. And depending on which class you're in, you may have left, which section you're in, you may have left this off. I'm sorry, if it seems like I'm out of it in this video, it's because, like COVID and that's causing headaches and a bit of fever and a cough and lots of other fun things. Yeah, Lane, it's not fun, is it? Anyway. So that's where we left off last time in one of my classes. What I want to talk about for the rest of this video is the idea of having a dominant strategy equilibrium state. For a dominant strategy equilibrium is going to be a strategy profile, meaning each player is going to choose a strategy in their game, in which each player is going to choose a strongly or weakly dominant strategy. So if you have a strongly dominant or weakly dominant strategy, play that, and if each player can choose that, that's going to give the game a dominant strategy equilibrium. If you recall, we said that an equilibrium state in the game is sort of a situation where every player is choosing the, quote, best option for them. And here's our first definition for what an equilibrium state can look like with everybody playing a dominant strategy. So let's take a look at these two games. Is there a way for, in the standard prisoner's dilemma, for both players to have a dominant strategy? I would say yes. If both players choose confess, that's strongly dominant, in fact, for each of them. And so, in the regular prisoner's dilemma, we're going to have a dominant strategy equilibrium of confess, confess. How about the uneven prisoner's dilemma? So in the uneven prisoner's dilemma, I claim there isn't a dominant strategy equilibrium. So why is that? Well, it's because player 1 doesn't have a dominant strategy. Player 2 does. They can confess, always confess, which is weakly dominant for them. But player 1 has nothing to do. There is no options to play for a dominant strategy. Because if player 2 chooses mirror, player 1 should choose deny, and if player 2 chooses anything else, player 1 should choose confess. And so in the uneven prisoner's dilemma, there is no dominant strategy equilibrium state. With the reason being because player 1 has no dominant strategy. This video still going? Hey, it's still going. Neato magneto. So, let's take a look at our dominant strategy equilibrium in the regular prisoner's dilemma case. So that's both players choose confess, which lands here. Does anybody notice anything interesting about this outcome, both players confessing in the regular prisoner's dilemma? Give you a second to think about it. Go ahead and pause the video here while you maybe think about that. Why is it interesting that confess is a dominant strategy equilibrium in the regular prisoner's dilemma? The answer actually is because if both players choose confess, that's going to be a strongly dominant strategy for each of them, meaning choosing confess is always better than choosing deny. But if both players end up choosing confess, then Madeline, it's not funny. Stop laughing at me. If both players choose deny, they could get a payoff of -1 each instead of a payoff of -8 each. So in other words, even though confess is a dominant strategy equilibrium, meaning it's both players choosing confess is strongly dominant for them, it's always the best choice, that still ends them in a scenario where both players are getting 8 years in jail. Whereas if both players had chosen their dominated strategy of deny, they would both come out better. with a strategy with a payoff of only 1 year in jail each. It's kind of interesting, and seems like a bit of a paradox, in that by choosing the option that's strictly better for you, you end up in a pretty bad square of the payoff table in the prisoner's dilemma, the -8 square. In fact, that's a square that, if the two players were cooperating, is probably the worst square to end up in, because they would have a combined prison sentence of 16 years in jail versus 10 if only one of them confesses, and 2 if both players deny. So just because something is called a dominant strategy equilibrium doesn't mean it's going to end up in, quote, the best square in the payoff table, because you could have something like in the standard prisoner's dilemma where that does not happen. Any questions or comments? So, last thing I want to do in this video is I want to look at a third game, which I made up myself. I call the iteration pack game. And what I would like you to do is to answer me a couple of questions. First of all, so in this game, player 1 can choose one of 3 actions. They can dine, dash, or sleep. Player 2 can choose one of 3 actions as well. They can eat, pray, or love. Don't ask me why I chose those. I was trying to be whimsical. So each player has one of 3 options, and I want you to just pause the video after I'm done talking here and do 2 things. First, see if you can determine if either player has a dominant strategy in this game. See if they, and if so, is it strongly dominant strategy or is it a weakly dominant strategy? And finally, I want you to answer one more question. It's kind of at the back of the packet here. By the way, I changed a couple of values in the table. This specifically says 010 and this says 011 if you're following along the packet. That's to help you make a point later on. So you might want to change that if you're taking packet notes. So first of all, does each player have a dominant strategy? And second of all, once you answer that, see if you can answer this question. Are there strategy profiles that are best I'm going to put best in air quotes here, for the 2 players to pursue? So go ahead, take a minute and pause the video and see if you can answer these 2 questions. I'm going to do an action pose. Okay, now that you've had time to think about these, let's evaluate. First of all, does player 1 have a dominant strategy in this game? I would say that yes, they do, and that the strategy of dine for player 1 is going to be a dominant strategy for them. Because if you look, dine, if player 2 chooses eat, dine is strictly better than dash and sleep for player 1. 2 beats 0 and 0. If player 2 chooses pray, then dine gives a better payoff than dash, and the same payoff as sleep. And finally, if player 2 chooses love, then player 1 gets their strictly highest payoff by choosing dine, because 1 beats 0 and 0. So dine is a dominant strategy for player 1 in this game. It's going to be strongly dominant or weakly dominant, Olivia. Oh, very clever of you, Olivia. Yeah, turns out that it's going to be a weakly dominant strategy. With the idea that if player 2 chooses eat, dine gives the strictly highest payoff. If player 2 chooses love, dine gives the strictly greatest payoff for player 1. But if player 2 chooses pray, then dine only ties with sleep for the best payoff, one either way. So if this one right here, for instance, was 0, then dine would actually be a strongly dominant strategy for player 1. But it isn't. So that makes it weakly dominant for player 1. How about player 2? Does player 2 have a dominant strategy? Well, if we look at it, Player 2 should never choose prey, because prey is a strongly dominated strategy. Because 10 loses to 12 and 12 if player 1 chooses dine, 10 loses to 12 and 11 if player 1 chooses dash, and 10 loses to 12 and 13 if player 1 were to choose sleep. So player 2 really shouldn't choose prey here. But eat versus love. Well, here's where things get interesting. If player 1 dines, eat and love come out to a tie for player 2. If player 1 chooses dash, eat is a better option for player 2 than love, because 12 beats 11. But if player 1 chooses sleep, then player 2 should choose love, because eat gives you 12 in that situation, whereas love would give you 13. So if player 1 dines, eat and love are equally good. If player 1 dashes, eat is better. If player 1 sleeps, then love is better for player 2. That means there is no dominant strategy for player 2, weak or strong. So does the iteration pack game have a dominant strategy equilibrium? Answer that down here. Dominant strategy equilibrium? Turns out the answer is no, as player 2 this time has no dominant strategy. So I'm sorry. This day has been a trial for me. Let's ask this other question. Are there any strategy profiles that if you and someone else were to play in the iteration pack game that you think are most likely to occur? When I looked at this, I kind of looked at the table for a little bit, and I tried to decide, I think that there are two payoffs, two strategy profiles that seem likely to me to occur, that being dine and eat, as well as dine and love. So why those two, you might ask? Well, my logic here was, I hope, fairly straightforward. The idea being that if player 1 wants to choose the option that's best for them, since dine is a weakly dominant strategy for them, player 1 should always choose dine. Player 1 should never choose dash or sleep, because they're just going to lose out on potential payoff that they could be making otherwise. So I'm going to kind of cross these out for player 1, because dine dominates that. So let's go now to player 2's perspective. If player 2 is thinking, all right, player 1's probably going to choose dine, so I should choose my strategy with that in mind. If you were player 2 here, would you choose eat, pray, or love? Well, I know player 1 is going to choose dine. I'm not going to choose pray, because I don't want to pay off 10. I would choose eat or love, because if I'm player 2, eat and love both give me a payoff of 12. And thus, that's why I say that I think dine, eat, and dine, love are the most likely strategy profiles to occur if the two players are behaving rationally, because player 1 should choose dine. They have no reason to choose dash or sleep. And knowing that, player 2 can choose eat or love. I guess for player 2 it comes down to, do you want to give player 1 a payoff of 2 or a payoff of 1? Maybe, I don't know, maybe player 1's a bit of a jerk. So it's like, oh, I don't want them, I'm going to love, and give them only a payoff of 1. I don't know why loving would give them a worse payoff, but who knows. On the other hand, it's like, nah, I'm going to eat player 1. Horrifying as that may be. That would give player 1 a choice of 2. But as far as player 2 is concerned, eat and love would give the exact same payoff, assuming player 1 is going to choose dine, which they really should. So I would say dine, eat, and dine, love are the most likely strategy profiles to occur, with the reason being, since player 1 should always choose dine, in which case player 2 should choose eat or love. So you might be sitting there thinking to yourself, oh, that's interesting, Dr. Gerstle, that we have these sort of two strategy profiles you came up with that you think are sort of the best strategy profile for the two players. But they weren't dominant strategy, but neither of these were a dominant strategy equilibrium for the game. In fact, the game didn't have a dominant strategy equilibrium because player 2 has no dominant strategies. So what's up with these two strategy profiles? Feel a little shady to me. Perhaps that they could be some other type of equilibrium we haven't discussed yet. And that is going to do it for our dominant strategies packet. When we come back in the next packet and in the next video, we're going to explore a new type of equilibrium called an iterated dominance equilibrium. And it's going to turn out that these two strategy profiles, Dine Eat and Dine Love, for the iteration pack game, are both going to be iterated dominance equilibria in this game, even though neither of those were dominant strategy equilibria. All right, that's going to do it for this video. I hope you're all doing well. I apologize for having to miss so much class like this, but yeah, sickness sucks. What can I say? Remember, you're all cool people.